Today we're going to be talking about classification. So let's assume, first of all, that we have some data points, xi, yi, like usual, and we have n of them, I equals 1 to n, and let's suppose that each xi is an m-dimensional vector, and our yi, and this is what makes classification, yi is either a 0 or a 1, meaning that it's in one of two classes. So our goal, so first let me say that that yi is called the label, or sometimes we also call yi the class of x. Each data point x is associated with a class. And so our goal for classification is, given some new x, classify it. As either a 1 or a 0. So I have this measurement and I want to say, is this person in this category or is she in that category? Or does this person have this sickness or not? And so you might think initially, oh, well, we can just do a regression where, our y's are 1. Oops, sorry about that. So we might do a regression where we have all these positive data points. Here, if this is x, this is in one dimension, and then we have values of 0. Here, we might say, oh, well, we can just do a regression. And then given some new x, we can see whether or not it's above 0.5. But it turns out that's actually not a good approach, because, for example, well, what if you have some positive points way out here? Well, then you might find that the best regression line is actually, given all your data, it's something like this. And, well, now all of a sudden, your cutoff is here for 0.5 and doesn't quite get these positives. So that's not good. We can't do regression. So no regression. We need to come up with a better approach for binary labels. So we have to do something else. So here's an idea. We can still use a linear function. We can still use a linear combination of the elements of x. So let's take W transpose x, some weighted combination of x, and squash it. So we get some real number, and then we want to squash it between 0 and 1. And this will represent a probability that x belongs to class 1. Probability that x in class 1. So if x is truly in class 1 and not in class 0, we want that probability to be really high. And so we'll say that the probability, more formally, that y equals 1 given some x is equal to some squashed version of W transpose x, where in classification, this function is called logistic. A very commonly used squashing function is called logistic sigmoid. And so now let's define more precisely what is the form of the logistic sigmoid function that's often used for binary classification. The way we define it is we raise e to this real value, W transpose x, divide it by 1 plus the same thing, e to the W transpose x. And I'm going to write another form that this can take, which is often used for analysis, 1 over 1 plus e to the negative W transpose x. And these are the same thing. You just divide the numerator and the denominator by e to the W transpose x, and you'll see that it comes out to the same thing. And so let's just reason about this for a second. When W transpose x is very large, well, these things will tend to be the same, and the 1 becomes insignificant, so the whole fraction gets closer to 1. So close to 1 when W transpose X is big. Some very, very high number, like positive infinity, you virtually have 100% probability that it belongs to class 1. And close to 0 when it's small. And the way to see that is if it's really, really small, like negative infinity, for example, well, you can take a look at here. This guy becomes extremely positive, and you have 1 over some very, very large number, and you basically have 0. All right, so now that we've defined the logistic sigmoid, let's just write out what the probability that y equals 0 is, given x. Well, by definition, that's just 1 minus the probability that y equals 1 given x, since there's only 2 outcomes. And that's equal to 1 minus, and let's use the second form from above, 1 over 1 plus e to the negative w transpose x. And if we do a little bit of math, we get e to the negative w transpose x over 1 plus e to the negative w transpose x. So that's the probability that y equals 0 given x. And now I want us to notice something. So I'll say notice. If we take the log, this is a little bit of a detour, but it's kind of cool. If we take the log of the probability that y equals 1 given x over the probability that y equals 0 given x, we're going to get something interesting. So let's just write this out a little bit more. So log of, and I'll fill in our form from above. So we get 1 over 1 plus e to the negative w transpose x. That's probability y equals 1 given some point x. And this down here is e to the negative w transpose x over 1 plus e to the negative w transpose x. Take the log of this whole thing. Well, first let's simplify the fraction. These cancel out, and I'm going to flip the sign of this, e to the negative w transpose x, bring it into the numerator. That's just log of e to the w transpose x, which, since every time we write log it's really base e, well, that's just w transpose x. And so what does this mean? It means that we can think of logistic regression as us regressing against the log of the odds that the class is 1. So this is the odds ratio, probability of 1 over the probability of 0. So you say, well, if there's, like, for example, if there's a 3/5 chance that it will rain and a 2/5 chance that it won't, well, then in that case we say that the odds are 3 to 2. And so you can think of logistic regression as us trying to find some weight vector that, when multiplied by x, gives us the odds. And notice that the range of a log function is the entire real line, so we don't have any problems giving continuous output with w transpose x. So that is one way to think about logistic regression. So I'm just going to write that, regressing against odds of class 1. So now that we have defined how we go about predicting whether or not a point is class 1 or class 0, namely by outputting a probability, let's talk about how we find the best W. So if you're not interested in exactly the math behind finding the best W, you can stop here, but if you are interested, we can keep going. So how to find the optimal W. So we have some training examples that we can look at. We can try to find patterns in the training examples. So how to find the best W given our training data? Well, as is our practice, we need to define some function that quantifies how good or bad a particular choice of W is. So for that, logistic regression uses the likelihood. And just a reminder, when we say likelihood, what we mean is the probability of the data given our parameters. In this case, parameters. In this case, just W. So probability of Y, probability that Y would be what it is given X in some choice of W. So let's write that down. We can actually write what the likelihood is. So we're going to multiply over all of our data points, I equals 1 to n. So the probability that yi equals 1 given some xi in our w, and we'll raise that to yi, and we'll talk about why we do that in a second, times the probability that yi equals 0, raise that to the 1 minus yi. And we want to maximize this. We maximize the likelihood. Find the W that maximizes the likelihood. And you'll see that if yi is truly 1 in our data set, well then we want this guy to be really high if we're trying to maximize. We want to say the probability of yi equals 1 is really high. We want W to tell us that. And if yi is truly 0, well, in that case, we want, and this whole exponent is going to be 1, and we want the probability that yi equals 0 to be very high. So you can see that in this likelihood function, select for values of W that follow the pattern in the data, which totally makes sense. All right. So to make things easier, what we're going to do is instead of maximizing the likelihood, we're going to minimize the negative, but not just the negative of the likelihood, but the negative of the log of the likelihood. And this just makes the math easier. And if you minimize the negative of the log likelihood, you're also minimizing the likelihood, since the log function is increasing. So let's write this down. It gets a little bit in depth here. So log of probability of y given xw is equal to the negative log of, and let's just write out what we wrote. So this whole guy, so probability that yi, and again this is over I, probability that yi equals 1 given xi and w to the yi times the probability that yi equals 0 given xi w to the 1 minus yi, the log of that whole thing. And now using the property of logs, I'm going to take some liberties here and rewrite this. So whenever you distribute a log through a product, it becomes a sum. And you can convince yourself of that if you need to pause the video. Just one of the properties of logs. So yi log of 1 over 1 plus e to the negative w transpose x. So notice that in addition to using the properties of logs, I'm actually plugging in what this value is. And remember, we defined that above. Plus, and I also brought down the exponents. Notice when we took the log, we bring down the exponents. Plus 1 minus yi. And now let's actually write down the probability of 0. yi equals 0. 1 minus yi log of e to the negative w transpose xi. Okay, and this whole thing's under the sum. So let's keep going. Let's actually simplify this even further. and that's equal to negative I'm going to write negative yi. I'm going to do some distributing here. So I'm going to take this guy multiplied by that. So negative yi log of 1 plus e to the negative w transpose xi. So where does that negative come from? Well, you remember when we take the log of a over b, we get the log of a minus the log of b. So I'm kind of breaking up that log fraction. Plus 1 minus yi times negative w transpose xi. And so that comes from here after we take the log of this exponent, negative w transpose xi minus log of 1 plus e to the negative w transpose xi. Okay, so if you need to take a minute and look at that, I did a little bit of rearranging in that step, but this is what we get. Now let's just notice here that we have negative yi times log of 1 plus e to the negative w transpose xi, and then we have a negative yi times the negative of that. So these actually end up canceling out eventually. So we'll cross this guy out with this and that. Actually, it might be easier if we expand this. So let's just keep expanding this for a minute, just for another minute. So over I, yi, negative yi log of 1 plus e to the negative w transpose xi plus negative w. I'm just going to FOIL these two terms. This would be a minus log of 1 plus e to the negative w transpose xi, and then plus yi log of the same thing, plus yi w transpose xi. And we're going to now notice, finally, that these guys cancel out, and this leaves us with negative over I. We get negative w transpose xi minus log of 1 plus e to the negative w transpose xi plus yi w transpose xi. And so this is our form of the negative log likelihood that we're going to work with going forward. And so what do we do now? Why did I just go through all that work? Well, if we're going to minimize, this is the loss with respect to w. If we're going to minimize that, we need to take its gradient with respect to w. And so putting it into that simple form, while we did all that work, now it becomes easier to take the gradient. Let's go ahead and do that, and then we'll talk more about why we do that. So the gradient with respect to w of the loss function, well, we're just going to distribute these gradients out. So we're going to take the gradient of each term in the sum. And I'm going to do a little bit of multiplying this negative sign through the whole sum, all in kind of one step here. So, so what we're going to do, this becomes sum over I of xi plus the gradient of this log term. So 1 over the thing inside, e to the negative w transpose xi, times that thing. So the derivative of 1 plus e to the negative w transpose xi is e to the negative W transpose xi times negative xi. I can use that dot as the dot for the I, plus, well, that should be minus actually, because we're distributing that negative through yi xi. And now notice that we can pull out an xi from everything. Xi, we get 1 minus e to the negative W transpose xi over 1 plus e to the negative W transpose xi minus yi. And we're almost done taking the gradient. In fact, we are done, but I want you to notice that this guy, the 1 minus, that's actually equal to the probability that yi is equal to 1 given xi and w. Because this guy is equal to the probability that yi equals 0. And that was what we defined above. So 1 minus that is this. And why is that significant? Well, that means we can rewrite this as the sum over all I times xi, probability that yi equals 1 given xi w, w minus yi. And so what we can see here is that this is the difference between the true value of y and our predicted value, our predicted probability. Difference between our probability and true value. And so you can tell that the points that are misclassified the most, so let's say the point's really 1 and I predict it's like 0.1 probability that that's true, well, the points that are misclassified the most, they contribute more to the gradient. And they get multiplied by the data point, xi. And we'll notice at the end of the day that this whole thing is it's an m by 1 vector, just like w is. So what that allows us to do is, well, first let's notice that there's no closed form for, if we set this to 0, there's no closed form for w. Like linear regression, when we set to 0, we could get an easy closed form for w by taking some matrix inverses, but in here there's no closed form because the logistic sigmoid function makes things difficult. But that's okay. It's okay that there's no closed form because we can do an algorithm called gradient descent. What that is basically you follow the opposite of the gradient with your vector w so that you can arrive at a minimum of the loss function with respect to w. So here's how the algorithm would go. So first you pick some w, you initialize some w. You think, I'm going to start out with this, and then you compute the gradient, which we've just defined above. And then you take your old w and you subtract some multiple times the gradient. Some multiple. And what that does is basically goes in the opposite direction. It takes your parameter vector w in the opposite direction of the gradient with the goal that hopefully you'll minimize the loss function. And in fact you will, because this gradient, the loss function is convex. The loss function is convex. So this will eventually reach a global minimum. And a quick quick note on this step size here. The best algorithms for gradient descent use the second derivatives of the loss function to inform us how much to step. So that's just a note there, but the overall point of this is that this is your gradient descent step, and so these would be done multiple times. Until you reach the minimum. So in conclusion, we have logistic regression, where we have a method for finding predicting the value that the probability that y equals 1 given x. We just take a w transpose x and we put that through a sigmoid squashing function. And so just a quick word on the sigmoid squashing function, actually. Whoops, sorry about that. So the sigmoid squashing function, it looks like this. So this is the sigmoid squashing function, and this is 0, this is 1, and the sigmoid squashing function kind of looks like this. So we squash it to a probability between 0 and 1, and then we get some probabilistic idea of how likely it is that our data point falls into class 1. The way we solve for the best value of w in our model is we take the gradient of the loss function with respect to w, and we perform gradient descent on that loss function till we get a w that minimizes the total loss. All right, and so our prediction, the last thing to say is that if we have a new data point, and this has already been said, but just to be clear, a new data point, it would be to take the sigmoid of our w that we get out of the gradient descent algorithm. We squash w transpose x new, and that is, again, equal to this. W star transpose x new. And this is equal to probability that x new is of class 1. And so maybe you'll say that if this probability is greater than 5, for example, I want to predict that it's class 1. And there's all kinds of literature on how to best select the threshold, and it really just depends on your application. All right, thanks.